question here is you have to find the reagent for this transformation. You are making ether with a double bond, right? So this is something that I want you to remember: the oxymercuration, demercuration, or more precisely, alkoxymercuration, demercuration. The reagent is a mercuric acetate, but not in water, in the methanol, because we want to make a methoxide there. So mercurium ion is going to be produced by that, but it's going to open up the methanol. It's going to be attacked on the more substituted side. If you got the alkoxide on that position, you cannot do this, right? You have to produce different alcohol. So some of the question you might think about is, what if you start with the same thing, but methoxy on that position, then how are we going to make it? That would be something that you should think about as well. But for this one, you see the nucleophile sitting on the more substituted side double bonds. That is a characteristics of the Markov-Nikel products. I guess you forgot that. So you need to cover that back. So Markov-Nikel products. So that means that you just can do the oxymercurations and demercuration. But this alkoxymercuration is the water using alcohol to make an attack. In the end, you have to get rid of the mercury. So sodium borohydride treatments will get rid of that, replaced by the hydrogen, so you're going to make it. So something that I want to think about is that's the Markov-Nikel product. What is the reaction to make an anti-Markov-Nikel product? That was all the questions that you think about that tonight. Next one is you're starting from the alcohol, but you're attaching this carbon chain. It almost looks very similar to the question you see yesterday, so I'm pretty sure you know what it is. This one, you basically have to make a nucleophile from the alcohol. You treat the sodium hydride, get rid of the hydrogen, it makes an alkoxide. That will be a nucleophile we have. You need to introduce the alkyl chain. So you can use it like ethyl bromide, or even you can just tosylate if you want to, anything that leaves. Then you can make an SN2 reactions. So these things are Williams and Lee synthesis. It's just an SN2 reaction with an alkoxide. So you can make the ethers. Epoxide opening is actually something that you have to pay attention to the reagent. Your reagents are nucleophile or the reagents are strong acid involved, then it will happen with the lead. So this is a phenyl magnesium bromide, benzene. pH is a phenyl, the benzene is a substituent, that's what it's referring. Phenyl groups are bound to the magnesium. That's the carbon ion right there, this strong nucleophile. We got epoxide here, but it's a differently substituted. On that side, just one carbon substituents. On the other side, we got two carbon substituents. So this side is a less substituted, this side is a more substituted. Less probably, more probably. If the nucleophile comes and make an attack, where is going to go? Is it going to go to there? Because in other cases, you see the more substituted side will attack, right? Or is it going to go to the other carbon? That's the question. Where is it going to go? So what I'd like to say is without protonation of the oxygen, this is a simply just nucleophilic attack, which is a very sensitive to the static hindrance. It will go to the less substituted side. So it should go to the less substituted side, opens it up. So you got the phenyl group sitting on the less substituted side, and the OH go to the more substituted side. I mean, then we pick up the proton in the second step and becomes an alcohol. So that is what I want you to remember for the nucleophilic attack of the epoxide, strong nucleophile. But if you do it in acidic condition with a very weak nucleophile, like alcohol or water, then the alcohol will not be able to attack this thing directly because it doesn't have a nucleophilicity strong enough to make it happen. Water is not doing either. So nothing's happening until this oxygen gets protonated. When oxygens are protonated, then oxygen will pull into the landscape from the carbon it's bound to, and then more substituted carbon will lose more electron density to an oxygen than less substituted side. So that's the reason the why the nucleophile makes an attack to the more substitute side, not because it really favor the crowded position, because of that carbon becomes a more electron efficient. There's a more electronic reason than static reasons. But if weak nucleophile makes an attack, this is a backside attack. So this methyl group sitting behind is going to push down, because a nucleophilic attack should involve the inversion of stereochemistry, right? The water makes an attack from the backside, so that's why the methyl below will be pushed up. So in the end, you're gonna have a methyl in the wedge. And then these are methoxy groups are sitting on the below until the OH that leaves out from the epoxide. So these two should be trans. Right? A lot of the stereochemistry and also the visual chemistry, which carbon of the epoxide nucleophile will make an attack, what stereochemistry is going to have in the product, things like that. It's so many things that you need to worry about. That's why we love this question.